failure of and failure of the plate. And the three important ones. And tensile strength and crushing strength. For this expression, PS, depending upon is it d square tau. This is for equals shear. 2 is double also given in terms of the table, and then the P for the inner rows the transverse pitch PT is given such that pitch for the zigzag, and it is equals to 2D for chain, and this PT is equals to 0.2P plus 1.15D between the outer row and the next row, whereas PT is 0.165P plus 0.67D for inner row and the next row. Has to be given as 1.5 times D, and the strap thicknesses. So T1 is 0.75 times T for wide strap. If you want to give a narrow strap, then is there, and our SUT is given as 26 ton per square inch, that is equals to 401.27 Newton per mm square. SUS is 21 ton per square inch is 324.0 1 Newton per mm square. So accordingly, using this, we will again our permissible things by sigma c is 1.5 times sigma t, and tau is sigma sus by factor of safety is used to determine the corresponding things, and based on that we have designed it. So this is for the design of the and then we also people talk but about joint and ascent with the relativity load, anything like this. This is within the load, within the plane of the rivets, and hence you have two types of things. One is primary shear, which is P dash I is equals to P divided by secondary shear. The secondary shear I is equals to, and such that Ri is the distance from CG, such that the secondary shear will balance the moment coming from this eccentricity. So that means is equals to P times E, or your C is given as P times E divided by summation Ri square. So your Pi double dash is given as P dot E summation Ri square with as J for all the summations times given Ri, multiply it with respect to Ri will give you the secondary shear. Then your total shear Pi square plus Pi double dash whole square will give you your total shear on the given rivet. So check Pi for the given corresponding shear strength. So Pi, your PS will be the and PS allowable. So that gives you, and this we have studied, and we have also looked into a couple of examples. So that is what in the kind of riveted joint. And today what we'll do is we'll in a similar lines we'll talk about the bolted joints. Unlike rivet, so today bolted joint case of riveted joints are riveted or welded joints are permanent because in order to cut rivets or to kind of unweld it or cut the metal plate in terms of riveting. Whereas for the bolted joint be replaced, the bolts need to move the nut and or the locking device and then the nut you can at any point of points. Bolts are temporary joints. Means are not permanent joints. In case some bolt is and replace it, so that is the much more kind of gives the flexibility as well as for the maintenance. So that is when it comes to the bolted joint, the bolt something like this. So if you look at it, this is your bolt head, kind of a shank, and this is your threaded region. And this is the nut, a kind of locking device at this place. So that generally for roots, what people do is device so that this nut doesn't fall off from the this bolt. So that is the reason this this locking device has significant importance, especially for the rotating components. For non-rotating components, people generally don't provide a locking device. It is mandatory, but it's okay to kind of devices. So anyway, class when we designed this, mostly your components you generally have to provide. So anyway, this kind of a bolt, the kind of the how much amount of uh, the kind of pre-tensioning you give it to this tightening it, your load also keeps. So right, the pre-tension you can shank of the bolt will also kind of. So this is a typical bolted structure, and as we have seen, this can be removed. But what happens is, since in this bolted framework, the cross section suddenly changes when it comes to this threaded portion. So that's the reason what uniform bolts are instead of strength. But it is advised to have bolt of uniform strength so that the fin be given place. So design bolts of uniform strength, there are for that So this is your shank diameter. And what happens in the core of this threaded region is smaller. It is to have this shank, this threaded to match the core of this, have a kind of uniform way to do it. In other way, you drill the material so that the net cross-sectional area after the hole is drilled in this region is will give same resistance as that of the threaded core region. So that is how try to get uniform strength, bolts of uniform strength in different ways. Now let us also see the kind of um, bolted joint. Because the maximum stress in the bolt is at the weakest cross section, and the weakest cross section would be on core dia. Here you can see there will be core dia on these threadings. So if you are matching this thing with the core dia, so we can write cross section as the area equal to, so the total divided by pi by 4 dc square. So it should be less than SYT divided of safety. So people also like to the kind of which have equal strength both in terms of tension as well as in shear. So in the shear, we know that the shear stress in the is P divided by pi dc into this is kind of this is the perimeter times the kind of the nut. So this is the kind of, so this area will resist the shear, which is the shear force P. So if we build same and there, that is and we want equally in tension on the shear stress divided by thing is equals to 4p divided by pi dc square. The height of the beam 0.5. So see 0.8 times of C. So it is this is the standard proportion based on the same thing. So this is what is generally used when somebody says that it is of a standard proportion. We will make use that the height of the nut is 0.4 times the T. Okay, so this is one thing which we'll make use in our further simulation calculations at later part. Now there are certain things which we need to make sure when we are making bolts are how the cutting has to be done for the thread cutting. So there are methods of making threads for the bolts, out of which there are only two popular ones. One is thread cutting, which is done using automatic machines that cut thread, and the other one is thread rolling, also called as cold forming, where threads are rolled from bar stock between the dies. Because of the thread rolling, improves the fatigue strength and hence reduces the stress concentrations due to radii at crust and root, and it also helps in less wastage in materials. So that's the reason this is more preferred and more reliable compared to the thread. So, and coming to the materials, So free cutting steels are used for lightly loaded small bolts, studs, and nuts, whereas plain carbon and alloy steels for high strength bolts. And if you need marine or kind of corrosion resistance, then are used for corrosion resistant or offshore applications. So these are the different materials that will be used. When we have threaded things, there is ISO thread, that is isometric screw threads are there, which we generally follow. ISO metric screw threads are there, in which the core diameter is 1.22687 times the pitch of the thread, and DC, which would be in this case is approximately is 0.8 times D. So as per this, we have couple of kind of a grades of steels as well as the grades of the bolts. So let us give the tabular things for the coarser ones as well as the finer ones with the basic dimension. This is for the coarser series. These are some ISO recommendations and their designations. So these are different grades of the thing of the bolts with the different diameter, pitch, and pitch by diameter ratios, and the corresponding the tensile area is given in this for the different calculations. Similarly, there is also fine series. So these grades are given as M6 cross 1, cross 0.75 and 0.25, which will be in between those the coarser ones, and it has different major to minor diameters and pitch and other things are given in this manner. So whenever somebody gives you the designation, you can look into this table and determine what is its corresponding major, minor, pitch, and the critical cross-section under the tensile can be obtained from this tabular form for future reference. So with this, what we'll do is we'll try to take up one example. So let us solve one example. So consider the two plates. These are the plates fastened by means of two bolts as shown in the figure. The bolts are made of plain carbon of 30 C8, which would have a yield strength of 400 MPa. Consider factor of safety is 5, and we need to determine the size of the bolts when or if capital P is 5 kilonewtons. So in this case, our known things is 5 kilonewtons. Our SYT is 400 Newton per mm square. Factor of safety is 5. So our allowable or permissible stresses under shear would be, let us permissible stress under tensile SYT for yielding is given by is sigma T SYT divided by factor of safety and permissible stress under shear is equals to SYS divided by factor of safety, that is 1/2 of SYT divided by factor of safety, that is equals to 40 Newton per mm square. is pi by 4 d square. So total bolt area is 2 times of it because we have 2 such bolts under shear. So and your PS is given as tau times area of the bolt, that is 2 times pi by 4 d square, right? But this has to be less than or equal to the total load. So that means 40 into 2 into pi by 4 d square is equals to 5 kilonewton. So D upon solving will be around 8.92, which we approximated to 9 mm. So this would be the size of each bolt that is required to take up this given load. So this is normal kind of things to get the things. So next thing what we'll do is to study eccentrically. So in this case, let us see an example shear. In the price, the is equals to C times Ri, and our C is very similar to the previous case, is given as, after substituting this into this, we can say that our C is given as summation of Ri square. So our Pi double dash is given as P into E summation Rj whole square with sum over all the things times Ri. So this will give you the things, and then your P bar is equals to Pi bar plus Pi double bar, which is a vector sum, or this means a vector. These things means vectors, or the magnitude of Pi is equals to square root of Pi square Pi, sorry, that's all. So that will give you the magnitude of it, which is very similar to that of the previous case. So for this case, let us see how that does look like. So this is this is the case. So this is the kind of, for a given load, let's say 1 2 3, given bracket 1 2 3 4 is the typical thing. And if you know the centroid, so the centroid can be obtained in this manner. If somebody wants to know how the G is, because not every time you can, this is a symmetric structure, so you can quickly say that this is the thing. If you want to find the centroid is also easily found out. The coordinates of the G can be done in this manner. You can take center as any one of the things. The coordinate axis can be located anywhere. From the coordinate axis, just measure the position of x1, y1, x2, y2, x3, y3, x4, y4, x3, y3. So one can find x bar is equals to summation ai xi divided by summation ai, and y bar is equals to summation ai yi by summation ai. Once you know this xi, x bar, y bar, this is x bar, y bar, your corresponding from here, this would be, here it is already. From the center, if you try to measure the distance from here to here, it is R1. This distance to that distance is R2. This is R3. This is R4. As we have shown that the eccentric load is equal to keeping a load at the things and a moment, which is P into E. If you look at it, this P is balanced by P1 dash, P2 dash, P3 dash, P4 dash. Whereas if you look at the movement P cross E, it is balanced by, which is in this thing is kind of balanced by the double dash, this and this, this and this. So this is in the clockwise direction. You can see this is partially compensated by the anti-clockwise. This is also anti-clockwise. This is also anti-clockwise. This is an, so sum of all these anti-clockwise movements would balance this thing. That is what we have even done it here, right? So sorry. The sum of all the moments should balance out the moment that is generated by the external load with an eccentricity. So that is how we have used this one, and we can calculate it as since this problem is kind of I mean more or less similar to what we have done in the previous riveted joint, very similar example. I am trying to just skip it for the kind of the time being, but I would suggest this can be easily obtained because this is very much similar to the eccentricity that you have seen it in the previous case for the riveted joint. So that's the reason I'm skipping the example. You go back, look into the yesterday's class, there is a similar example where the eccentricity of the bolted joint is there. So, but the next type of eccentricity today I'll be dealing with it is when the eccentric load is perpendicular to the axis of the bolt. And in this case, I will try to give you an example and we'll work out on that example. So next topic is So in this case, let us have a look how does this perpendicular to the axis of the bolt. So this is a case of a scenario. You can see this bracket. If you are seeing from the side angle, this is a kind of a bracket. Unlike the previous case, the bracket and the bolts are in the same plane. In this case, the bracket and bolts are in the same plane, whereas in this, the bracket is in the kind of, you can see the bolts are in this direction, the bracket is in this. So that means your load, this load is perpendicular. This is the plane of the, so let me show you. This is the plane of the bolt. But your load is there in this plane. Your plane of bolt is this fellow. So whereas in the above case, this is your plane where the bolts are there, and it is the same plane where the load is also acting on it. So that's the reason it is different from this scenario. So this has to be dealt differently compared to the previous case. This is the plane of the bolt and this is the plane of the load. What you're seeing here is the plane of the load, or you can see this is the plane of the load, and so this is the plane of the load and this is the plane of the bolts, because in this plane, right, it is there. In this view, it looks like the load is acting on it, but if you look from the side view, you can see that this load is acting at a distance e from this plane. So that's the reason this is an eccentric load perpendicular to the axis of the bolt. And because of this loading, what will happen is this bracket would try to bend. This would bend such that as if it is hinged at C. So because of that, this bolt is subjected to an axial tension of by axial deformation by delta 2, and the top one will be, all the top bolts will be subjected to axial tension of delta 1. Because this is a rigid plate, we can assume in this manner. Okay, so compared to the stiffness of the bolts. So that's the reason, assuming that this deformation is like a plane and hinged at the C, we'll make use of this thing to kind of calculate our the shear stresses and tensile stresses and the equivalent shear stresses coming from the tension. And then we'll use that thing to design the case when we are having such kind of scenarios. Okay, so for that, let's assume so by assuming bracket and the steel structure, so this is the bracket and this is whatever is the steel structure is rigid, then only this plane sections remains plain, and this kind of an approximation will come into the picture. Secondly, the bolts are fitted in reamed and grounded holes so that a perfect tension can be enforced onto this bolts. The third thing is bolts are not preloaded. This is a very major kind of a assumption. That is, your bolts are not in initial tension. This is very difficult to enforce, but let us assume it, because when you are tightening it, it would, at most of the cases, it will have some pre-tension, but theoretically we are ignoring at this point of time. So in this case, let us call all the upper bolts as the 1 and all the lower bolts are as 2. And as I said earlier, this would this would loading would kind of create a moment such that it is hinged at C, and hence it would give a delta 2 at this second location and delta 1 at the things. And from C, the distance of the center of this bolt 2 is L2. The distance from the this bolt hinge, this kind of a hinge where the plate is rotating, it is to the center of the bolts, and the top one position is L1. Okay, so now let us calculate the direct shear with these assumptions. There is no problem in the direct shear, which is straightforward. But when it comes to the stretch delta I, we will say that they are proportional, or they are linear to the distance it is there from the hinging point. So that means we can say that our Pi double dash is equals to C times Li, and such that our P times E is summation of the moment which is in the off plane is balanced by the tension in the differential tension in the bolts. So Pi double dash Li dash Li. So that means we can, since in this case we have 2 bolts at the second location, 2 bolts in the upper location, we can write this one as 2 times P1 double dash L1 plus 2 times P2 dash L2, because we have 2 bolts at the second location and 2 bolts at the things. This 2 comes from there, and hence using these 2 we can say that our C is equals to P times E divided by 2 L1 square plus L2 square. Once you know the C, again we get back into this and we determine the Pi double dash, which gives us the tension. So then we can say that our tension sigma T in the bolts is given as Pi double dash divided by the area of the bolt. In this manner, we'll calculate the tension in the things. But this is tension, and this is this will give you the shear. The shear is given as tau is equals to P1 dash by air. But this is shear and this is tension. So in order to solve, we need an equivalent tension or equivalent shear. So we can write that as, based on the principal shear stress theory or the principal stresses, we can say that our sigma 1 is equals to sigma T by 2 plus sigma T is our principal stress, and our maximum shear stress is given as the radius of the Mohr circle, which is sigma T by 2 whole square plus tau square. And this maximum shear has to be less than tau allowable. And if we just use this thing, then we can design our kind of a structure with an eccentric load. So for this, let us consider following example. a wall bracket is attached to the wall by means of 4 identical bolts, 2 at A and 2 at B below, location A and this is location B, such that they are with respect to the dimensions are mentioned in this figure, and assuming that the bracket is held against the wall and prevented from tipping about the point C by all the 4 bolts. Assume sigma T allowable is equals to 35 Newton per mm square. Determine the size of the bolt based on maximum principal stress theory. So in this case, we already know that our capital P is 25 kilonewtons and our eccentricity is 500 mm. Our, let's say, LB is 50, LA is 550 from C location. So, and sigma T maximum or allowable is equals to 35 Newton per mm square. So our direct shear will give P1 or P8. So there are 4 bolts as we have seen earlier in the previous thing. So this is very similar to this one. There are 4 bolts, 1, 2, 3, 4. So let's say these are location 1 or location A and location B or location 2. So let me put it again here. A is analogous to 1 location, B is analogous to second location. So P1 dash or P2 dash in this case is equals to total P divided by 4 because there are 4 bolts, 2 this side and 2 this side and 2 the other side. So that is 25, 3 divided by 4, that is equals to 6250 Newton. Similarly, the direct shear tau in this case is equals to, in any given bolt, is given as pi by a, so which is given by 6250 divided by kind of pi by 4 d square, or we'll just call it as a for now. A is the direct shear, which is in terms of Newton per mm square. Now coming to the secondary stresses. The secondary stresses in this case are tensile in nature, that is P1 double dash is equals to P into E L1 divided by 2 times L1 square plus L2 square, that is equals to 25 into 10 power 3 into 500 into 550 divided by 2 times 550 whole square plus 50 whole square. That would give something around 1127.5 newtons, and P2 will be much lesser because P2 is proportional to L2 and L2 less than L1. Therefore, P1 double dash is critical. So that means we can just get over with P1 is sufficient. So now if we find out what is the, based on the maximum principal stresses, our sigma 1 principal stresses, sigma 1 is equals to sigma t by 2 plus sigma t by 2 whole square plus tau square. So that is equals to sigma t. We have to get down the sigma t in this case. From P1 dash we can say that sigma t is equals to P1 double dash by A, that is equals to 1127t.5 divided by A, which is pi by 4 d square. So which I put it back here. But we know that this is resisted by 2 bolts. So on the top at the 2 locations, so it is divided by 2A. So it is 1127.5 by 2A plus R. I mean, it's only the plus, which is the major one, plus 1127.5 by 2A whole square plus 6250 by A whole square will give us 140.50.6 by A Newton per mm square. We know that this is the maximum sigma 1. This sigma 1 has to be less than sigma t allowable, so that is 140.50.6 by A has to be less than 35. That implies A is equals to 401.45 mm square. For this tensile area, if I go back and look into my series table, you can see that an M30 is okay and M24 is lesser. So we need, our value is somewhere 401, which falls between these two. So 401 is this. So we cannot go with 24. We have to go with M30. So M30 standard bolt size is required. So in this manner, you will try to design the size of the bolt. Okay. So with this, we'll complete the kind of bolted joints. In the next class, what we'll do is we have another special case is there, which I would like to quickly do before we take a break. So let me just give you, because this is a special scenario. Okay, let me just quickly finish that one, because sometimes you may get it to design a circular basis. So next, threaded fasteners for circular bases with eccentric loading. In this case, the loading would look something like this. So you have this is kind of circular base, and you have these kind of bolts which are inclined at different things, and you still have an eccentric thing. Instead of a flat rectangular kind of a base, here you have a circular base, and in the circular base the location of this 1 2 3 4 are a little bit crucial. So I will quickly let you give these things, and we'll not do an example, but I'll quickly give you a design procedure to work for such things. So if you want to solve something like this, you can see that since the location of all the 4 bolts are at different places, you have delta 1, delta 2, delta 3, delta 4 are also varying in nature. And depending upon this inclination, let's say alpha, your entire things would kind of change. So let me quickly give you the design procedure. Before we go further, we have to make certain assumptions. That all bolts identical, so that we don't differentiate between one to other. Second thing is, both the bearing and the structure are kind of rigid. That means only bolts are kind of deformed. In that case, this kind of deformation is possible, where this sections remains flat as it is, and only the bolts are kind of deforming. And there is no preload or stress concentration in the bolts, and if there are any shear stresses, they are relieved from dowel pins, which are shown here. So with this assumption, again we know that the direct shear will pi dash is equals to P divided by N. That is pretty simple. Whereas in the other cases, here the moment generated by the eccentricity, P into eccentricity in this case is L. P into L is again given by Pi Li, and our Pi is proportional to Li. That means this is equals to summation C Li square. So our C is given by PL by summation Li square. And for suppose if we want to check if we have an alpha, which is, let's say this bottom angle is, the one is at an angle alpha from the vertical passing through the center of this base, then based on that we can give our different this L1, L2, L3, L4 calculations as below for that configuration only. So let me call it as figure B. This is B figure, this is A figure. So this is C figure, this is D. So for figure B configuration, the calculations of L1, L2, L3, L4 would be such that L1 is equals to A minus B cos alpha, L2 is equals to A plus B sin alpha, L3 is equals to A plus B cos alpha, L4 is equals to A minus B sin alpha, and our L1 square plus L2 square plus L3 square, no matter what, would always be equal to 4 times A square plus 2B square. So that is a good sign, and accordingly our resistant forces would be PL A minus B cos alpha divided by 2 times of, so I take 2 common from these two, is 2A square plus B square. And for even number of bolts, our P1 would always be PL A minus B cos alpha N into 2A square plus B square. And P max will always be A plus B N 2A square plus V square. And once you know the thing, then you can apply your principal shear theory, and you can obtain the corresponding allowable stresses can be applied. So this would be very useful if you are kind of doing an eccentric loading with a circular base, such that the angle is alpha from the vertical for the first one, as shown in the figure 2. With this, what we'll do, we'll finish the bolted joints. I thought of starting the shafts also today, but since it is going late, what I will do is tomorrow we will start shafts and shaft couplings. So after that, I have only kind of springs that is left. So I think within the next week we'll able to finish the syllabus,